MOSFET characteristics. In this video, I consider only N-channel depletion type MOSFET. The electrical symbol are as follows. Here's gate, here's drain, and here's source. And ID is current flowing through this drain. ID also equal to IS because the gate current equals 0. The curve here's ID is current. The curve is this. So here we have VT, we call it threshold voltage. And if horizontal is VGS in volts. Okay, now if VGS smaller than VT, then in this region in this region ID equal to 0. If VGS smaller than VT, and in this region VGS smaller than 0, in this region we call depletion mode. Depletion mode. And if here's 0, if VGS greater than 0, in this region it is called enhancement mode. This is N-channel depletion type MOSFET. Now, by the way, we can also in comparison with enhancement type MOSFET, the ID VGS transfer curve is this. Okay, I just for comparison, this is N-channel enhancement type MOSFET. Now, and for enhancement type MOSFET, VT is here. VT is here. VT. So this is N-channel enhancement type MOSFET, and this curve is N-channel depletion type MOSFET. Now, here we use threshold voltage VT. Okay, we write down here. VT has many names or notations. For example, VGS off. This called gate source cutoff, and also has another name, or VP. VP is pinch off voltage. Now, this point, when VGS equal to 0, the current ID has name IDSS. IDSS. And this curve is quadratic and is described as following. ID equal ID SS 1 minus VGS VT equal IDSS VT minus VGS and equal ID SS VT square VT minus VGS square. And equal IDSS VT square. I changed the order because this square I can change the order. I can put VGS in the front and VT behind. And we define the coefficient in front bracket as Kn. So Kn is defined as IDS as VT square in datasheet IDSS is called 0 gate voltage drain current. If we define IDSS divided by VT square as Kn, then we can write ID this form as following as ID equal to Kn times VGS minus VT square. This formula is exactly the same as the formula we describe enhancement type MOSFET. To make everything clear, we make the following table. So we list here depletion type MOSFET and enhancement MOSFET. For depletion type MOSFET, VT sometimes used as VGS off, and this value is smaller than 0. And for enhancement type MOSFET, VT is written at VGS threshold, and this number is greater than 0. And sometimes VT is written as VP. I write down the absolute value VP and VGS off. The reason is this, because some author in the textbook write VGS off as VP, and some author write down VGS off as minus VP. So for you, as long as you make sure VT here is negative for depletion type MOSFET, then you're okay. Now, how to find Kn? For depletion type MOSFET, Kn is equal to IDSS divided by VT square. This is the formula to find Kn. But for enhancement type MOSFET, Kn you can find from the graph in the data sheet. From graph in data sheet, they usually give you this type of graph. So ID as function of VGS, but this curve sometimes they give you at different temperatures. Okay, different temperature. So what we do is here, from this graph, you can find VT, threshold voltage, and you pick up any point, some point in somewhere, and this point VGS star, and ID is ID star. Then you have this number VGS star and ID star, and you have VT. You can plug in this formula. So VT you plug in here, and VGS star you plug in here, and ID star you plug in here. Then you use this formula, you can find Kn. The mathematical formulas for enhancement type MOSFET is the same as for depletion type MOSFET. So I can write down again, I can repeat again here. The formula is the same for both enhancement type MOSFET and depletion type MOSFET. They are the same. So the formula is as follows: 1, cut off region. If VGS smaller than VT, then ID equal 0 for all values of VDS. Second, try out the region. If VGS greater or equal than VT threshold voltage and VDS smaller than VGS minus VT, then ID equal Kn 2 times VGS minus VT times VDS minus VDS square. Three, saturation region. Saturation region, if VGS greater or equal to VT, and also VDS greater or equal VGS minus VT, then ID is equal Kn VGS minus VT square. So we have cutoff region, tryout region, and we have saturation region. Now, I'm going to give you examples. Okay. Okay, example. VT equal minus 4 volts. You see, when given VT equals minus 4, then you will know immediately that this MOSFET is depletion type MOSFET. And Kn equal 1 milliamp divided by V square equal 1 time 10 to the minus 3 A divided by volts square. The circuit is this. Okay, I write down the circuit. The circuit is characteristic circuit. This is G gate, and Ig equal to 0. Now we have here depletion type MOSFET. So this is S. This D, green. And for the polarity, VDS, we define as this is positive, this negative. So this VDS. If VDS is greater than 0, that means the voltage at D is greater than voltage at S. Now here is ID, and ID equal to IS because current through IG equals 0. And I define polarity as following for VGS. This is positive, this is negative. If VG as positive, that means the voltage at G is greater than the voltage at S. Now, I have Vt and I have Kn. I can plot the characteristic curve from the Matlab code. And here is Matlab code. So this is our code. This code is the same code as enhancement type Matlab code. So we plug in here Kn equals 1.0, 10 to the minus 3, and Vt equals minus 4. So I just plug in two numbers. Vt is minus 4, Kn equals 10 to the minus 3 amp per V square. So I have Kn, I have Vt. Now VGS I can start from minus 3 and minus 2 and minus 1 and 0 and 1 and 2. For the plotting, okay, I slow down here. Okay, this is the Matlab code, the first part of Matlab code. And this is the second part Matlab code. So I need to change the plotting range, and from 0, this is the ID curve, ID range from 0 to 0.04 with increment 0.004. I only need to change these values to make the graph looks nicer. So this is the second part of the Matlab code. Then I'm going to show you the graph from this code. Okay, this is the second part of the code. So this is the I-V characteristic of MOSFET. In this case, I plot Vt equals to minus 4, the threshold voltage is minus 4, and the Kn equals 0.001 amp per volt square. Then VGS minus 3 and VGS minus 2 and VGS minus 1 and VGS 0, VGS to 1 and VGS 2. And the drain current is in this vertical axis. Okay, I'm going to show you another example. The second example is this. Example. Example. Depletion MOSFET has A, D, SS equal 12 milliamp, 12 milliamp, and VP equal minus 4.5 volts. And calculate the problem is that calculate the drain current at gate source voltages of A 0 volts, B minus 2 volts, and C minus 3 volts. And we assume that if the device is in saturation, okay, solutions. All we need to do is find Kn. So in this case, Kn equal IDSS divided by Vt square equal 12 milliamp divided by Vp square equal 12 milliamp minus 4.5 volts square. Zero 0.5926 milliamp volt square. And in our formula, in our Matlab code, we always use SI unit. So I need to change to milliamp to amp. 0.5926 time minus 3 amp per V square. So we have the Kn. Now I want to find Vt. Vt is threshold voltage. So equal, in this case, equal to Vp equal minus 4.5 volts. So for depletion type MOSFET, you want to make sure Vt equals negative minus 4.5 volts. So once I have Kn and Vt, I can plug in these two numbers into our Matlab code. Okay, in Matlab code, we need to change these two values. Kn 0.5926 10 to the minus 3, and V threshold is minus 4.5. Okay, now the problem they ask for gate voltage 0, minus 2, minus 3. So I modify my gate source voltage as starting from minus 3 and increment 1 volt unto 0. So I have here minus 3, minus 2, minus 1, 0. That's it. I also need to change the plotting range. Here the plotting range. The maximum of current is 0.016. I need to modify here, but this is trivial. It's simple. This is the second part, the program. And then for the text, I need to modify here. I need to modify here to plot the Kn and Vt in the proper place. So here is the second part of the code, and here is first part of the code. Now I have the code, then I can show you the results of Matlab Plot. Here's the Matlab Plot. This. So I have Vt minus 4.5 and the Kn equal this value in SI unit. Then from MATLAB I can identify at VGS minus 3 this value. From MATLAB you can use your cursor put on here anywhere place, then you can get this value. So this is the answer for here. The problem is this: gate source voltage equal minus 3. The answer equal 0.00133 amp. For this problem, minus 2, when GS equal to minus 2, I got this answer. And when GS equal to 0, here I get this answer. 0.012 amp. But the problem, they didn't ask you minus 1 here, but I plot here as minus 1 here anyways. So I do not need to show you the number here, because the problem did not ask minus 1. So they only ask 0, minus 2, minus 3. So 0, minus 2, minus 3. So this is the answer. This answer, and this answer, and this answer. Now, I have a remark here. Remark. In our formula for Matlab code, we have for tryout region we have ID equal to Kn, then this factor, and also in saturation region we have ID is Kn VGS minus VT squared. So the thing here is, in our formula on in Matlab code, we use Kn. Okay, the remarks this. Okay, our notation we use Kn, but some other textbooks they use Kn, they use K. Okay, they use K, and some other textbook they use K divided by 2. So you need to identify what value, but we use Kn. Okay, for example, if they have notation on here is K divided by 2. Okay, for example, here this, what the other notation is this? Other notation is ID equal K divided by 2 VGS minus VT square. In that case, you identify this K divided by 2 as our Kn, this Kn. But some other textbook, they write down here is ID equal to K VGS minus VT square. Now, in that case, his K equal our Kn. So this, as long as you find our Kn, then you find threshold voltage, then you can plug in the Matlab code and the formulas we have, then you get the answer.